Hi everybody, this video covers the second part of Section 1 in Chapter 7, and we are going to multiply and divide rational expressions. So as I mentioned, we're going to talk about reducing rational expressions, multiplying them together, and then dividing them together. Okay, now take a look at this particular fraction. This is the fraction of 24 over 18. And it turns out that both the numerator and the denominator have common factors. And of course we can figure that out by doing a prime factorization, which is what we've done here. 24 can be written as 2 times 2 times 2, which is 8, times 3, which is 24. And 18 can be written as 2 times 3 times 3 to get 18. Also notice that if you take a look at this prime factorization, you notice that both the numerator and the denominator have a common factor of 2 and a common factor of 3. And if we group them, we can find that they are equal to 1, and we can go ahead and we can divide them out. And as a result, we can multiply the 2's together up here, and we get 4 and then 4 over 3. So we reduce fractions by identifying and grouping factors that are common in the numerator and the denominator, recognizing that those grouped common factors equal 1, and then we can basically eliminate them. Okay, well, it turns out that the same applies to rational expressions. For example, take a look at 4x cubed minus 4x divided by 2y times the quantity x minus 1. Both the numerator and the denominator have common factors. Now that might not be obvious, but if we actually factor out the greatest common factor here, which by the way would be 4x squared, we will be left with a 2x squared over y, a common factor of 2 in the numerator and a common factor of 2 in the denominator, and then the common factors x minus 1 in the numerator and x minus 1 in the denominator. As a consequence, these cancel out, and we are left with 2x squared divided by y. So rational expressions behave just like integer expressions in the sense that all you need to do to reduce them is you need to identify factors, group them together that are common in both the numerator and the denominator, and then recognize that those grouped common factors are equal to 1, and then we can basically just cancel them out. So how does that work in an example? Well, here we go. Here we have two common. Here we have the rational expression of 2x minus 10 and 3x minus 15. And notice that the numerator has the greatest common factor of 2. We can go ahead and factor that out, and then we have x minus 5. Similarly, the denominator has the greatest common factor of 3. We can factor that out, and then we are left with 3 times the quantity x minus 5. Now note that the numerator and the denominator have the common factor of x minus 5. As a consequence, they are equal to 1, and this would be equal to 2/3. And we know that this is reduced because this fraction right here has no common factors. Here's another example. Now notice that we have y minus 10 in the numerator and 10 minus y in the denominator. So they look different, but also notice that they are also opposite of each other. If I wanted to, I could write this as negative 10 plus y divided by 10 minus y. Well, that may not be very helpful, but what if I factored a negative 1 out of the numerator? Then I would have negative 1 times 10 minus y, that should be a 1, not an I, 1, there we go, times 10 minus y divided by 10 minus y. And if I wanted to, I could write that as negative 10 minus y divided by 10 minus y. This would be equal to negative 1, and we would have a negative 1. And I want you to pay attention to this because you will see this a lot in your homework assignment. And that brings us to our next topic, which is multiplication with rational expressions. Now, multiplication with rational expressions behaves just like multiplication with integer fractions. For example, 2/3 times 3/4 is going to be equal to 2 times 3, multiplying the numerators together, divided by 3 times 4. Okay, but then we need to simplify common factors, or simplify by removing common factors. And notice that we have a 3 in the denominator and a 3 in the numerator, so they factor out, and we will have, or they basically equal 1, and we will have 2 divided by 4. But notice we still have common factors. For example, 4 can be written as 2 times 2. So these can be canceled, and we will have what you would expect, 1/2. Well, it turns out that multiplication of integer fractions are actually the same as multiplication of rational expressions, because essentially an integer is basically nothing more than a polynomial degree 0. So basically the approaches that we use for multiplying integer fractions are the exact same approach that we can use for multiplying rational expressions. The big thing here is that we want to be careful we want to first factor both the numerator and the denominator. That way it's easier to recognize common factors. With that idea in mind, we also want to multiply both the numerators and the denominators together, both in factored form, once again, so it is easier to recognize common factors. And then, of course, you want to reduce the product by dividing out those factors that are in common in both the numerator and the denominator. We know for a fact that the rational expression is reduced to smallest terms when the only common factor is 1. And of course, once again, since we are dealing with rational expressions, no denominator can have the value 0. That means that q cannot be 0 and s cannot be 0. Okay, well, here is our first example. Here we want to multiply and reduce, if possible, the product of these two monomials. Well, the first thing that we can do is we can express the second monomial, or we can express both monomials in factored form, particularly as it pertains to the constant values. So that would give me 5x squared y divided by 3 times xy cubed times 2 to the 4th x cubed y squared divided by 3 times 5xy to the 4th. And then if you multiply all this together, we are going to have 5 times 2 to the 4th times x squared times x cubed times y squared. And then in the denominator, we are going to have 3 times 3 times 3 times 5 times x times y cubed times y to the 4th. Okay, now notice here that we have a 5 that cancels. We have a 5 in the numerator and the denominator. Also notice that we have an x squared here, and we have 2 x's down here, so they cancel. And also notice that we have y times y times y squared, which is y cubed, and a y cubed down here, so they cancel. And what we're left with is 2 to the 4th, which by the way is 16, times x cubed divided by 3 to the 3rd, which is 27, times y to the 4th. And that right there is our answer. Cool. Okay. So how does it work if we're dealing with, instead of monomials, fractions that are polynomials? Well, here we go. Once again, our first step, however, is to factor each polynomial. So to factor this polynomial, this is going to be equal to 3 times the quantity x minus 1, because it has the greatest common factor of 3. This has the greatest common factor of x, so this would be basically x times x plus 1. This right here, you may recognize this as a perfect square, so this would be x plus 1 times x plus 1. If you wanted to, you could also write this as, you could also have written this as x plus 1 squared. And then finally here we have a greatest common factor of 3, which leaves me with x squared minus 2x plus 1. That too is a perfect square, and that would be x minus 1 times x minus 1, or you could have written that as x minus 1 squared. Okay. So the multiplication problem in factored form would look like this. 3 times the quantity x minus 1 over x times x plus 1 times x plus 1 times x plus 1 divided by 3 times x minus 1 times x minus 1. And then when we multiply these two together, when we multiply these two fractions together, we multiply the numerators and then together and then the denominators. And if we do, we will have 3 times x minus 1 times x plus 1 times x plus 1 divided by 3 times x plus 1 times x minus 1 times x minus 1. And now we need to get rid of the common factors. Well, notice that we have a 3 and that 3 is a common factor in both the numerator and the denominator, so they can go. There is an x minus 1 here, which is in common with one of the two x minus 1s in the denominator. And then finally, there is an x minus 1 in the denominator, which is common with one of the two x minus 1s in the numerator. Okay, once we've dealt with all of those, what do we have left? Well, we have we have x plus 1 divided by x times the quantity x minus 1. And that would actually be your answer for this particular problem. So that is multiplication in a nutshell. Notice that is not much different than when you were dealing with fractions back in middle school or high school. And that brings us to our final topic, which is division. Now, recall that when you are going to divide one fraction by another one, what would we do? Well, we take the reciprocal. That's the reciprocal. Reciprocal. And then we multiply. And that's what we've done here. It turns out that 3/8 divided by 4/12 is equal to 3/8 times 12/4. And of course, and then we can multiply the numerators together to get 36, the denominators together to get 32. We can do our prime factorization, and notice that we have 2's in common, we have a set of 3's in common, and the result, of course, is 2/3. Well, division by rational expressions is the exact same way. Here I basically labeled our expressions as P, Q, and R and S, but these are basically just names for polynomials. And the division problem is equivalent to multiplying PQ by the reciprocal of R over S, or S over R. And if you do, this is what you get. You get P times S divided by Q times R. So how does this look in terms of examples? Well, here we go. Now remember, we're doing division, so the equivalent multiplication problem is going to be 12x squared y divided by 10xy squared times xy cubed divided by 3x to the 4th y. All right, cool. Now we need to do the factorization of our coefficients. So the factorization of 12 is going to be 2 times 2 times 3. Almost forgot the 2 there. X squared y. And then the factorization of 10 is going to be 2 times 5. 2 times 5. Xy squared times, well, the factorization of x, well, there's nothing to factor here, so that's just xy cubed. And the factorization of a prime number is, hey, the prime number, 3x to the 4th y. And that should look like a y cubed. Now, you could actually go ahead and do some reducing right here if you wanted to, and there's no reason why you can't, but to stick with my script, I'm not going to go ahead and I'm not going to do that. Instead, I'm going to multiply the numerators and the denominators together, and if I do, I will have 2 times 2 times 3 x squared x y y cubed. And then over here, I'm going to have 2 times 3 times 5. 2 times 3 times 5 x to the 4th y squared y. All right, now I notice here that I have factors that are in common. I have a 2 that is in common with the 2 and a 3 that's in common with the 3. That's cool. And then I can go ahead and start combining exponents. And that would give me 2x cubed y to the 4th divided by 5x to the 5th y cubed. Using my quotient rule, I will see that this would be equal to 2/5 times x to the minus 2, and then times y. Of course, I can't have negative exponents, so I need to bring that down to the denominator, and if I do, I will have 2y over 5x squared. I actually have two more examples before we go on to Hawks, and here is the next one. Once again, we want to divide and reduce if possible, and we want to change this division problem into the multiplication problem, and we can do that by flipping the second fraction and then multiplying, and that would give me x squared minus 8x plus 15 over 2x squared plus 11x plus 5 times 4x squared minus 1 divided by 2x squared minus 5x minus 3. Okay, now we need to factor each term. Well, this term right here is we have a leading coefficient of 1, so this is a 6.1, 6.2 type problem, so we need to find factors of 15 that sum to negative 8, and that would be negative 3 and negative 5. So we can write this one at the first term here as, or the numerator for the first fraction as x minus 3 times x minus 5. Or x minus 5 times x minus 3, if you forget to write the x minus 3 first. As far as the denominator is concerned, well, notice here that this is an AC type problem, and we need to find factors of a times c, or 10, which sum to 11. That, of course, will be 10 and 1. Okay, if we apply all that, and if we do the math, what you will find is that this will reduce to x plus 5 times 2x plus 1. Now, the next term, well, this actually is a difference of squares, so this will be equal to 2x plus 1 times 2x minus 1. And then finally, for the last one, we need to find factors of 2 times negative 3, or negative 6. That sum to negative 5, and that would be negative 6 and 1. And if we use those, we will have, after solving all that, we will have x minus 3 times 2x plus 1. Now, once we multiply these two together, what we're going to have is x minus 5, x minus 3, 2x plus 1, 2x minus 1, all divided by x plus 5 times 2x plus 1 times x minus 3 times, once again, 2x plus 1. Now we can cancel out those factors that are in common in both the numerator and the denominator. Notice here we have a 2x plus 1. I have one here, I have one here. They can cancel out. Here I have an x minus 3 and another x minus 3. And that's pretty much all that we can cancel. So our answer is going to be the quantity x minus 5 times the quantity 2x minus 1 divided by the quantity x plus 5 times the quantity 2x plus 1. And that's pretty much it. Now, if you wanted to, you could possibly expand out the numerator and write this and write the numerator in a standard form. Typically, you do not want to do that in the numerator, in the denominator. Basically, expanding the denominator in standard form does not do anything for you at all. However, expanding the numerator into a standard form might be helpful, especially particularly if you have to add this to another rational function sometime later. And this brings me to my last example in this at least in terms of the lecture slides, and it is this. Okay, and this also happens to be problem 10 in your homework, or a version of problem 10 in your homework. So once again, to convert this to the equivalent multiplication problem, we want to flip the second fraction and multiply, and that will give us 5 divided by 3 times the quantity n minus 3 times 3 minus m over 7. Okay, well, do we have common terms here? Well, no, we don't. But notice that this is written in this. The numerator is the opposite of the denominator, so I could write this as negative. I could write this right here as negative the quantity m minus 3, which is actually what I'm going to do. And then that would give me 5 times 3 over the quantity m minus 3 times negative m minus 3 over 7. Now I have common, and now when I multiply this together, I'm going to have negative 5 times the quantity m minus 3. Over here, I'm going to have 21 times the quantity m minus 3. All right, awesome. And then notice I have now I have a common factor that I clearly see, which I can cancel out. There they are. And then my final answer will be negative 5 divided by 21, which was exactly what I was looking for. Okay, so that's it. That's all that I have for this part of the video. Stay tuned, and I will get Hawks up and running. Okay, so here we are in our famous Hawks in OneNote environment, and let me go ahead and start my practice. Okay, so let's try this problem. So here we want to factor the coefficients in the numerator and denominator, and that will give us 12t. We can write as 2 times 2 times 3, and then we have our t squared, over 5s squared, which would be 5s squared since we can't factor the 5, times 3 times 5 for 15, s squared, divided by 2 times 3 for 6, and then t. Now when we multiply all these together, we will have 2 times 2 times 3 times 3 times 5 times s squared times t squared. That's the numerator. And then in the denominator, we are going to have 2 times 3 times 5 times s squared times t. Now notice that we have common factors in both the numerator and the denominator. For example, we have this 2 here, we have this 3 here, and we have this 5. Okay? Also notice that we have an x squared in the numerator and an x squared in the denominator, so they can go as well. So that leaves us with 2 times 3 times t squared divided by t. So we could use the quotient rule to figure that out, or we can just realize that we have t times t up here and t down there, and one of them will cancel as well, which gives us our answer of, well, 2 times 3, which is 6, times t. So the answer here should be 6t. There we go. Okay. Let's take a look at this problem. Here we have 5 divided by 4 times the quantity x minus 7 times 7 minus x divided by 3. Okay, notice here that I can write 4 as 2 times, the factorization for 4 is 2 times 2. The rest of these are prime. So this would become 5 divided by 2 times 2 times x minus 7 times 7 minus x divided by 3. Now that everything is factored, we can go ahead and multiply the numerators and the denominators together. And if we do, I'm going to have 5 times the quantity 7 minus x divided by 2 times 2 times 3, or 12 times the quantity x minus 7. Now notice that even though the binomial term are not the same, you can actually tell that they are opposites of each other because each one has the terms are the same, but the signs are different, or the terms are the same, so the only exception being the signs. So we can actually factor out a -1 from the numerator, and that would give me -5 times x minus 7, and over in the denominator we will have 12 times x minus 7, The x minus 7's cancel, because they are common in both the numerator and the denominator, and reduce to 1, and we are left with negative 5 over 12. There you go. And now we move on to some division problems. Okay, so let's take a look at this problem. Now, the equivalent multiplication problem is going to be essentially 24b squared divided by 3a squared times the reciprocal of the second fraction, which will be 21a squared divided by 6b cubed. Okay, now we can do our factorizations, and for the first one we will have 2 times 2 times 2 times 3 times b squared divided by 3a squared. And then for the next one we will have 3 times 7a squared divided by 2 times 3b cubed. And then when we multiply the numerators together, we will have 2 times 2 times 2 times 3 times 3 times 7b squared divided by 2 times 3 times 3 a squared b cubed, and I almost forgot my a squared up here. My apologies. Okay, so now we have factors that are common in both the numerator and the denominator. For example, we have a 2 here, a 2 here, a 3 here, a 3 there, a 3 here, a 3 there. We have an a squared common here and an a squared there, and that gives us 2 times 2 times 7, 2 times 2 times 7 times b squared over b cubed, and then this will be equal to, well, 2 times 2 times 7 is 28, and then we will have, and using the quotient rule, we will have 28b to the negative 1 power, and that will be equal to 28 over b, because we cannot have negative exponents. Well, we can, but Hawks won't like it. Okay, let's see if this is right. 28 over b, and there we go. And let's do this for our last problem. Here we have 7 minus s over 6 times 4 times the quantity s minus 7 over 7. The equivalent multiplication problem is going to be 7 minus s over 6 times the reciprocal, which will be 7 divided by 4 times the quantity s minus 7. Okay, we do have a few things that we can factor. We can write the 6, that's supposed to be an s, not a 5, sorry about that. We can write the 6 as 2 times 3 times 7, and then we can write the 4 as 2 times 2 s minus 7. And now we can multiply. That will give me 7 times the quantity 7 minus s divided by 2 times 2 times 2 times 3 times the quantity s minus 7. Now notice that the numerator, the binomial term in the numerator is basically the opposite of the binomial term in the denominator. So I can factor out a negative 1, and that will give me a negative 7 times s minus 7. And I can go ahead and multiply this stuff out. That will give me a positive 24 times s minus 7. And as you can see, I have an s minus 7 in the numerator and s minus 7 in the denominator. They cancel, and I am left with 7/24, negative 7 over 24. Okay, and that's it. And that is all that I have for this particular video. If you have any questions, please feel free to contact me. This is Bob Boyle.